Hi all, today I want to explain something about related to numerical application in our life, drug distribution. This video animation is prepared by Ikram and Muhammad Shami. So, there are three main objectives of this video. First, we want to solve the real-life problem using various numerical methods. Second, we want to compare the error of these numerical methods. And finally, we want to determine the most accurate method between these numerical methods. So, what are we going to do? This is our general idea. First, we find the solution using various numerical methods. Then, we find the exact solution. After that, we find the errors of each numerical method. And finally, we can conclude which method is accurate. Before that, let's watch a video about drug distribution.
We're flowing through the vein. What you don't see is that the vein is filled with plasma that flows with the circulation. This is how the drug distributes through the circulation before arriving at the site of action. The drug circulates from the stomach into the portal venous system. The portal venous system sends the drug to the liver to be metabolized. This is called the first pass effect. The drug enters the heart, then exits to go to the lungs, then comes back into the heart, and then goes out of the heart through the arteries. The drug will circulate in the arteries to its site of action.
Here is a motivation. Can we calculate the concentration of the drugs in human body? The answer is yes, of course. So let's see the example of real-life problem. A drug with K equals to 0.03 is to be administered in doses of Y naught equals to 4 mg. Calculate the drug level Y at time t equals to 5 and assume that the step value H equals to 1. Can you guess the equation that we will use? Here is the equation. Yt prime equals to negative k yt. Before we start to solve the problem, let's analyze the question. First, k equals to 0.03. Second, Yt equals to 0 is 4 mg. 3, H equals to 1. And 4 is Y equals to T equals to 5 is Y. So, let's solve the problem. So, we solve the problem using various methods of numerical method. So this is the first one, Euler method. Here is the general formula of the Euler method. By the formula previously, we solved the problem. So the first iteration, we get 3.88. The second iteration, we have 3.7636. And the third iteration, we have 3.650692. We repeat the same method for fourth and fifth iteration. We get, for the fourth iteration, 3.541171, and the fifth iteration, we have 3.434936. So, we have Y when t equals to 5 is 3.434936 mg. So, we solve the problem using the second method, which is improved Euler method. This is the general formula of improved Euler method. By the previous formula, we can solve the problem using improved Euler method. So the first iteration, we have 3.8818. The second iteration we have 3.767093, and the third iteration we have 3.655775. We repeat the same method for fourth and fifth iteration, where the fourth iteration we have 3.547747, and the fifth iteration we have 3.442911, and we get y when t equals to 5 is 3.442911 milligram using improved Euler method. Next is the third method, modified Euler method. So this is the general formula of modified Euler method. By the previous general formula, we can solve the problem. So the first iteration we have 3.8818. We have 3.767093. The iteration we have 3.655775. We repeat the same method for fourth and fifth iteration, where for fourth iteration we have 3.547747, fifth iteration we have 3.442911, and finally we get y. The value of y when t equals to 5 is 3.442911 milligram for modified Euler method. And the fourth method we use Runge-Kutta order 4. This is the general formula of Runge-Kutta order 4. By the formula, we can solve the problem. So the first iteration we get 3.881782, and we have 3.767058, and we have 3.655725, and we repeat the method for fourth and fifth iteration. Fourth iteration we have 3.547682, and the fifth iteration we have 3.442832, and finally we have the value of y when t equals to 5 is 3.442832 milligram by using Runge-Kutta order 4 method. This is the comparison of the final answer from various numerical method. Where Euler method we have 3.434936, the improved Euler method we have 3.442911, the modified Euler method we have 3.442911, and the Runge-Kutta order 4 we have 3.442832. Which one is the most accurate? To find out, we find the exact solution from the differential equation. Yt prime equals to negative kyt. We modify it, and finally we get yt equals to y naught exponential negative kt. We substitute the value of y naught equals to 4 and k equals to 0.03 into the equation, and then we get yt equals to 4 exponent negative 0.0t, and for yt equals to 5 we have 3.442813. This is the value of exact solution. After we get the value of exact solution, we find the error of all the numerical methods. So this is the formula to find error of each numerical method, where error is modulus exact value minus numerical value over exact value. This is the calculation. So we find out that Euler method has 0.002288% of error. improved Euler method have 0.000028%. But also from modified Euler method have 0.000028% of error, and Runge kata have 0.000006%. So this is the summary. From four method we find the y when t equals to 5, and then we find the error of each method. So you can look up. Here is the conclusion. Since Euler method has the highest error, thus it can be concluded that this method is the least accurate. And since improved Euler method has lower error than Euler method, then this method is more accurate than Euler method. Since the modified Euler method has lower error than Euler method, then this method is more accurate than Euler method too. And finally, we found that since Runge kata for method has the least error, thus it can be concluded that this method is the most accurate. So at the end of this video, we found out that the most accurate method is Runge kata 4 because it has the smallest difference to exact solution, which is 0.000019, and also have the least error, which is 0.00006%. And that's all. Hope you all understand and enjoy our video. Thank you.